Okay, awesome. I think we're just about ready to get started. I see a few more people trickling in. Cool. Okay. Hi, everyone. I'm Rohin, and
I'm Caroline.
And we're founding engineers at Runhouse, an open source Python library and startup based out of New York. We're here, just sharing our knowledge with you here today and about our company and also just about our perspective on the ML infra universe and stuff there. So just to get going, Runhouse was started because we believe that despite a lot of the tooling built for the industry, ML development has a ton of engineering friction involved and it's far from seamless. So there's a few key problems we want to dive into and then we'll dive more into what Runhouse does. So without further ado, let's get started. So before joining Runhouse, I spent 3 years working on ML infrastructure at a computational neuroscience team at Meta. One of the key problems we faced were the barriers between research workflows and production workflows. It would take weeks, if not months, to get ideas out of a researcher's notebook into a productionized model that could be shared for user acceptance testing, product demos, or for collaboration with other organizations.
And for me, prior to joining Runhouse, I spent several years working on the PyTorch team with our founder and CEO, and we saw similar problems across the board from our users. Those of you who have worked in the AI ML space have certainly seen these before. Let's dive into it.
Cool. So yeah, like we said, I mean, all of us have here working in the space of analytics, research, data science, machine learning, AI, whatever it may be. These two universes consistently exist in these workflows. So researchers, data scientists, and ML engineers have to frequently jump between two worlds, research and experimentation environments and production environments. It's the friction between these two environments that leads to a ton of lead time added to the delivery of any robust AI and ML solution. On the left, we have research and experimentation environments. These are most commonly Jupyter notebooks, but you also see sandbox development environments meant to mimic production. On the right, we have our production environments. These include orchestration frameworks, DAGs, things that wrap your code in decorators, YAMLs, and containers that freeze your dependencies and environments so that they can be reproducible and shared. And so compared to deploying things in production environments, the advantage of local development is quite obvious. It's fast iteration and high debuggability. This is what we've been doing for years. When you program, you change your code, you see new results and changes immediately. However, the local machine usually doesn't have the same powerful accelerators that are available to an ML team via a shared compute cluster. Moreover, it's really difficult to share your work with your teammates. The most common workflows to date are still copy-pasting or checking out another researcher's branch from a Git repo or whatnot. Then discrepancies between users' environments often manifest, and it can take a while for someone to replicate the same results as you because different dependencies installed or different things in play. Moreover, you may not even have access to the real training data. Due to privacy rules, many organizations will not allow real data to end up on local machines. There are tools that have tried to enhance the notebook experience to be more collaborative, but generally, to actually use your code anywhere, you have to go through a bunch of productionization steps and then share productionized components with your teammates. It takes significant engineering work to turn your components from your Python notebook into code that can actually run in a pipeline, and even more work to turn it into a simply shareable service that runs on a cloud machine. On the other hand, production environments generally run within powerful compute clusters, and the runs are much more reliable and reproducible. Since nodes are set up from scratch, they're not dependent on any local state. It's easier to take the results of your experiments and modeling with others, and share them with others, and easier for them to take your pipeline, maybe make a few changes and run it again to see changes in the results. However, there's clear disadvantages to these production environments, as many of you guys definitely are aware, is that they're really low on debuggability. You'll often see users taking a push and pray mentality where they run the pipeline, see it fail, make a change, run it again, only for one component to fail right away from the start. And then once it works, it becomes super sensitive to bugs and gets frozen, since trying to track down bugs within a large ML pipeline or data pipeline is pretty challenging. The code is often overly packaged, filled with decorators and tool-specific classes and primitives that make it difficult to translate this packaged Python back to normal, runnable Python. In fact, most of the time, you can't even run this code easily locally. You need to use some sort of special command line tool provided by the provider that you're using, or some YAML or config in order to do that. Finally, a lot of these production infrastructure tools are configured to run within a specific Kubernetes cluster or cloud environment that they've been configured in, and therefore are tied to the infrastructure that they're on. Moving between AWS to GCP or from on-prem to cloud, requires a ton of infrastructure migration work. And moreover, like many of your teams and organizations probably are operating in multi-cloud environments where you're using tools and clouds from different providers. In this case, you have to write special wrapper code to run different parts of your ML pipeline on different cloud platforms or tools. It's pretty much impossible to interoperate within these cloud environments and very hard to have visibility into what all your resources are doing. So for all the aforementioned reasons, moving between these two environments is super challenging, generally requires a team of ML engineers with considerable knowledge of both infrastructure and ML research being done in order to translate things effectively from your research world to your product world. This takes power away from researchers and ICs themselves who should be able to share their work and reproduce it easily. And even more so, it's really hard to take a productionized experiment or pipeline and change large things about it, getting back to the actual training or anything like that. So going back to the research world is really hard. So to reiterate quick, the main issues that come from this like ML fragmentation that we've observed in the ecosystem is no ML flywheel. The pipelines and DAGs are super hard to iterate on. Moreover, there's not really an easy way to share like in-progress work. If a researcher has gotten a model or a script working and they want to quickly share it with product teams or customers to figure out what exactly may be wrong with it early on, they still have to go through the productionization work, which could take a while, and at that point, the work may be rendered useless. Secondly, lack of infrastructure flexibility. Many of the DAG frameworks or compute frameworks are built to operate, again, within a single cloud cluster, single region. This prevents you from taking advantage of compute credits and discounts across regions without doing a bunch of extra work, and ties you to specific tools or point solutions. And then lastly, something that we've barely even dreamed about is end-to-end management and visibility of all your compute. It's super hard to get visibility in what your compute is actually being used for. So much of the kickoffs of these jobs are just push and pray retries. If you're using environments across many clouds and tools, you have different dashboards across all of them that show you the actual utilization of your compute across these areas, and you don't know what resources are where. And so that's just a large challenge. And so we spent a lot of time thinking about these problems. We want to make putting ML code on real infra accessible to the masses, and we believe that there are a few key principles that are missing that it should follow. Firstly, the code that you run should be infra-agnostic, annotating functions code with specific operators or decorators, or wrapping them with a bunch of YAMLs generally makes it way harder to move between tooling or clouds. But if the code is infra-agnostic, it allows you to easily spread your pipelines and work across many tools without having to package them up for specific environments. Next, there should be high iteration speed available for 90% of the ML process. We understand that containers and frozen images and frozen environments are totally needed for production-grade model serving or for like critical model training pipelines. But for the first 80 to 90% of the ML development process, scientists and engineers should be able to have really nice, robust develop experience, and they should be able to, it should be as smooth as developing locally. And next, with the rise of popularity in AI development, there's a ton of demand for compute resources everywhere. Modern ML frameworks should have actual visibility into how a team's compute is being used, or if you're in a large company, how different teams are utilizing their compute, and how these teams' resources are distributed over all the different providers that you work with. And then finally, ML development should certainly be fully multiplayer. It shouldn't be so hard to collaborate with your teammates. You shouldn't have to choose between either sending someone a Git SHA that has a branch of your code, or sending them a fully robust pipeline that you had to create in order to collaborate. Any Python of mine that I'm running on like a remote machine or cluster should be able to become a service that I can share within seconds.
To summarize, we see the solution as something that is consistent, reproducible, and having quick feedback loops. Something that is infra-agnostic and serves both research and production well. This is something that PyTorch does well. It's both flexible and modular enough for research and experimentation, yet at the same time, it's also stable and has support for production deployment. It works the same across research and production, OSS and private, and even across different hardware types. And so as we develop Runhouse to be a Python native infra-agnostic interface into your ML infrastructure, we drew inspiration and parallels from PyTorch to achieve our goal. For starters, we wanted Runhouse to work in just Python. Python is built in anywhere you want to deploy or run ML. You can develop anywhere you want, whether this be an IDE or notebook, and then deploy anywhere, orchestrator, containers, CI/CD. By having a pure Pythonic solution, we also avoid the need to have to learn or set up DSLs, configs, and decorators. ML is a rapidly developing field where the tooling quickly goes stale, but Python is much more durable. By removing the need for specific tooling, your ML code also becomes easier to iterate and debug on. Furthermore, this enables reproducibility and accessibility. If you're trying to share a program with others, what this might look like today is sharing a README full of CLI commands and configs for how to set up an environment and then run their script. Instead, what if you could just publish your Python code, have it contain all your hardware and dependencies, and be confident that this code will run the same on anyone's laptop. And just like how PyTorch lets you send a tensor to CUDA or to CPU, Runhouse lets you send your Python function or class to a specified compute. There's no need to move code around, package it into Docker containers, or translate it into a pipeline DAG first. This benefits both your local development workflow as well as your research and production iteration loop. For local development, it makes it easy to take your code, send it, and run it on remote compute. Anytime you want to debug, you can just make a change locally and instantly redeploy it on your remote compute. For the overall research production loop, you're now directly able to send and run research code on your production compute. And because the Python code, the underlying Python code is the same, you can now easily extract your code back into your local development flow to iterate on and push it back into production. PyTorch also introduced the concept of eager mode, in which individual operations act as independent modules, and they're also immediately executed as soon as they're encountered. This is in contrast from graph mode, in which operators are first synthesized into a graph that is compiled and executed as a whole. Eager mode is advantageous because of its modularity. It is easier to iterate on smaller portions than as a whole. So production ML today can kind of be viewed as similar to graph mode, in which you have your traditional production DAG that packages and compiles components together. Here, each oval in the graph represents a piece of your ML pipeline that has already been translated and packaged into a container that is suitable for production. Then we further link these components together to form a DAG and schedule it for execution through an orchestrator on a cluster, waiting for all necessary resources to become available before it runs. DAGs are great if the program is fully working and we never need to change anything, but if the pipeline fails, tracing it to the source of error, debugging it, retranslating, rerunning the pipeline, it all becomes a tedious and time-consuming process. And because everything is bundled into orchestration, it's practically impossible to share subcomponents of your pipeline. Each component now has some glue code linking it to a previous or a future step. Anytime you make a change to your step, you add some more glue code and it's no longer modular. Different pipelines now have different glue code, producing different behavior and artifacts, and another team's basic data preprocessing step no longer works for you. Meanwhile, this is what an eager execution model using Runhouse looks like. Each component can be as simple as a Python function that is executed as soon as it's encountered. Each component is modular, it's also isolated, and this makes it possible to send each component to its own specific provider, making it easy to optimize for cost and availability. Any glue code you have can sit cleanly between these functions rather than being packaged and bundled together. So now, if you want to modify and iterate on a part of the pipeline, you only need to modify and rerun that individual component without needing to worry about how it fits into the general pipeline as a whole. And also, because each component is now decoupled, it contains only the information necessary for itself and also all the information for itself, it's now easy to share and reuse. Now, when you have your data preprocessing service, another team can easily call into the service without needing to worry about anything that might have been added to your component. And now going back to the first diagram we showed with some of the advantages and shortcomings of the various stages of ML, but following the principles that we just discussed. On the research and experimentation side, we maintain our fast iteration and high debuggability, but we now also have access to more powerful compute for running our modular components. Collaboration and reproducibility is also easy because we can just share our isolated Python service. On the production side, we still have our powerful compute and stable environments, But because we've now replaced our overpackaged orchestration nodes with more modular Python components, it's now easy to debug production code as the code just runs as is. This is also flexible across infrastructure types. You can orchestrate across clusters, regions, and clouds. To summarize, this is the state that we have with Runhouse. Your research and production code is now identical and exactly reproducible. It can be used across teammates and across infrastructure. And as a result, you save both time and cost. You also bridge the gap between research and production. So because development code now runs as is in production, the need for packaging and translation is removed. And because production code is now the same as development code, it's easy to update and iterate on. And to be clear, we're not suggesting that you no longer use containers or DAGs where needed. These are often still necessary for shipping and testing production models and ML services. However, the experimentation and iteration loop that happens in ML development shouldn't need to depend on this production-grade tooling.
Cool. So, we've touted a lot of features, so I feel like it wouldn't be complete without at least showing you guys a demo of how this all works. So let me just see if I can get this. Cool. So let me know if you guys can see this. I'll zoom in. Cool. OK. So I've made a fake training function here. But as you can see, it's a normal Python function. There's no magic happening. There's no decorators. There's no YAMLs attached to this. There's no containerization or anything like that. Literally, it's just a Python function, takes in a parameter, and it's going to solely calculate a fake loss that I'm just randomly generating. And then the point is that I can just deploy this on my own cloud compute really easily with Runhouse. Again, we're not hosted. We're connecting you to your existing AWS, GCP, on-prem, whatever compute that you have set up. So you see, it's really just like 4 lines of code to run this on the cloud easily. This first one, I bring up a really simple box on EC2. You see here, I've specified that I want a box that has CPU, 2 of them. I can also pass in things like A10G:3 or :4, sorry, and just get any box that has 4 A10G accelerators. I've also specified provider AWS, but if you have many of them set up, you can just specify provider cheapest, and it's going to get you the accelerator that's cheapest out of all the environments that you've linked. And so now this is a cluster, and this is what's going to come in handy with our .2 framework that we've kind of modeled after PyTorch that we're going to show you in a sec. Next, we set up an environment with all the required dependencies. In this case, I only needed TQDM. Everything else is just built in Python. But I need the TQDM library in order to show the loading bar. And so we can also here pass in environment variables, secrets, anything else that the code needs to run would be installed on the machine. We're also supporting Docker containers, so if you want to run your code within a Docker container, we'll be able to pass that in if you guys are still operating in a Docker environment. So next, I'll actually take this function, and I'll just wrap it in a function factory and send it to the box in this environment, and I'll get back a remote function. And I can call this the same way that I would call this. I could pass parameters, I could not pass parameters, it doesn't matter. And it returns the same way that it would if it was running locally. So this is kind of the magic that we've been touting, that you shouldn't need to do a bunch of extra work to extract results from your code and whatnot. And so yeah, why don't I just show you guys real quick. Cool, I think this is kind of, it's kind of hard to see the bottom, so I'm gonna move it up here, perfect. So I'm just gonna run this, and as long as the Wi-Fi is good, we shouldn't have any problems. But yeah, it's gonna refresh the status for the cluster, and this is, again, this is in my AWS environment, so it's just, it's not like we're sending anything to Runhouse. Again, this is open source, you can pip install it. We're not doing taking any of your code or data in this situation. So whenever this connects. Sometimes, depending on the internet, it can take a few to recognize. Cool. So it found the machine, sends my code to it. The first part is just the cold start with AWS, but yeah, it's usually pretty fast. And then sends a function, calls it. You see the blue text is the standard out that's coming from the remote machine down to my local machine. It looks like the function's running locally. And if you really wanted to, you could SSH into the server itself and figure out state and stuff like that. And then it received a final result from the remote function and just displayed it here. So that's the quick demo. Again, we'll have time at the end for questions, but we're going to move into the rest of the talk again. So I'm just going to full screen this. Oh. One sec. Thanks for bearing with me. And let's continue.
Okay, cool. So now that we understand some of the core development principles in building Runhouse, and that we've also seen it in action with that demo, I'll give a brief overview of Runhouse's core components and how they all fit in together to enable flexible and reproducible services. So there's a few crucial components for being able to deploy remotely and reproducibly, more specifically the compute, the environment, and of course the code itself. So Rohin briefly went over this in the example, but I'll cover the options a little bit more in depth here. So compute refers to your own infrastructure, and this is where you want the code to be deployed to and run on. This could be a static cluster you already have up. It can be an on-demand cluster that you want us to spin up for you. This is using your own cloud credentials, or it could be like a Kubernetes or a SageMaker cluster. The environment consists of any setup that you want to have prior to running your function. So this can include any packages you want to install, a working directory you want to sync over, environment variables, API secrets, setup commands, anything really. Each environment is then run, has its own process on the cluster. And this can happen directly on the cluster, or it could also be in its own specified content environment. And of course, we have our Python code. This can be like a function or a class, and it's just exactly what your development code looks like. You don't need to change anything. We just simply wrap it in a factory function, and then it's now able to be sent to the cluster and environment. So with these components, we can now reliably deploy, save, and share a function. So to deploy the function, we use the .to API. When you send a Runhouse function or class to a cluster, we set up the environment as specified, and then we sync over your local code, including any relevant dependencies and code files onto the cluster. There is no serialization involved. The code is just a copy of your local code that runs on the cluster. And then once it's been sent to the cluster, you can call the function as if it were a local function, except that it now runs on the specified remote cluster and environment. So any inputs that you send are also passed to the server, and all the results from calling the function are later sent back to you. And now it's basically a service that you can call over and over again. As long as your cluster is up, your service stays up. You can now recall your function with no new setup time, and anytime you make a change to your local code, you can instantly deploy it back. You can also save your Runhouse resources, which saves down any metadata necessary to reconstruct the service. For instance, if you save down a remote function, this will save down the function signature on the cluster, and it will also save down your cluster and environment information. You can also share resources with your teammates, or you can publish them to public, and when you do this, you can specify the level of access, such as read or write. And now that you've deployed a function, and you've either saved it or shared it with a teammate, they can simply reload the function by calling it by name, and immediately they have access to your remote service. So this doesn't recreate or redeploy the function for them. They actually just have direct access to the same service that you just deployed on that cluster. It also has an endpoint that one can directly call. If you can recall, one of our key points earlier was to be able to turn Python code into a service that runs remotely and is easily callable. And we build this out for you without you needing to write your own fast API wrappers. Being able to access a function by name also means that your functions are more maintainable. You can change the backend compute, for example, and it's ambiguous to the user.
Cool. So this whole save and share concept of Runhouse that Caroline just went through brings us to the other key non-open source component that we call den. So after you run save on any of your functions, we store a lightweight config of them on our servers. But don't worry, the actual code data does not leave your machines. And again, you don't need to do this. That's only if you have a Runhouse account set up and whatnot. But it comes with a few advantages. Firstly, you can search all your existing resources, regardless of which cloud environment they're in or type of compute they're on. This is especially useful to you guys who are working in multi-cloud environments. If Runhouse was used to dispatch your code to the infrastructure, we can see it. And so therefore, you'll be able to see all your functions, models, data, whatever that's across different cloud tools that you guys use within different cloud environments. And then next, as we've shown, you can share your functions and clusters and environments with teammates. You can do this directly with just emails. You can also create groups and organizations. And so this goes along with search and discovery as well. If you have teams within a company and a team has a bunch of resources, you can view the clusters that your team has, the functions that your team has set up, et cetera. And then finally, we can also track when functions are updated and called. So there's lineage of when a function was updated. There's lineage of how many users are calling a function. This is useful if I set up a really quick internal service to share with a bunch of ML people in my team, and I want to see who's using my pre-processing function, my evaluation, my benchmarking, whatever it may be. I can share that really easily. I didn't have to do any crazy production setup, and I can track who's using it and how often. And then finally, perhaps the most useful thing, again, slightly cut off by the captions, but is auth and access control. So like we said, when you share this, the person has to log in with the Runhouse token, and you basically already set up your Python function as a service that has authentication such that only a person logged in with their email will actually be able to access it. And so being confident that only the users that you selected can access your functions is a huge asset, and it allows you to turn any code that's running on your remote compute into a full-fledged authenticated service accessible anywhere. So yeah, and then as you understand more about our approach to ML infra, you'll see that being the universal access point into your various cloud machines has some clear benefits. Firstly, we can greatly optimize costs by pooling all your compute resources in one place. This allows you to get the best size machine for the job, the cheapest machine, between regions and clouds that you have. Think malloc over all of your compute rather than just over the single region, single cloud clusters that you've set up. Moreover, like we've already mentioned, the Runhouse paradigm makes it far easier to serviceify your repeated work. And so if there's ML pipelines that are creating nodes that are all doing the same thing over and over again for perhaps an initial pre-processing step or a final evaluation step, these things can easily be turned into services that can just still be called in native Python without any additional setup or creation of a client or anything, but live on a different machine and can be updated easily. And then finally, like I already said, we can see how resources are being used and who's calling them. But moreover, we get actual compute utilization information by using Runhouse. You can see which teams are underutilizing their compute, how many resources they're using in which clouds. And so this is a huge thing for some of our enterprise conversations where people want to know which teams are using compute effectively and are wasting compute and where things are needed more. And so just by having everything in one place, and dispatching through Runhouse, you can get some of that inspection and visibility. And with that, yeah, thanks for listening. If any of these concepts resonated with you, please reach out to us. We're an early stage company. We're trying to establish this design paradigm. It's quite different than the things that have been set up in the space today. And so we have a bunch of examples up on our site that just run immediately if you have Runhouse installed. And again, it's open source and published on PyPy, so you can pip install it right now. And remember that Runhouse interfaces with your existing compute, so you need a plugin Cloud Credentials to set it up. We do offer 5K in AWS credits program to anyone interested in experimenting with Runhouse who doesn't have a personal cloud account that has money and whatnot. So yeah, reach out to learn more. Our emails are there, our website, etc. And yeah, we can open the field to questions. If you want to talk more closely, feel free. Caroline and I are here for the next several days at the conference, and we are happy to chat about anything technical, customer facing, whatever you guys are interested in. So thanks, everyone.